So, last class I have covered vertical stress distribution on a horizontal plane and as well as vertical stress distribution on a vertical plane. Then considering point load, it has been extended to find it out vertical stress by a line load. Then vertical stress distribution by a strip load, again considering point load, then it has been extended taking into a small portions, then it has been integrated over that strip zone minus b by 2 plus b by 2. Then is your vertical stress below the center of a uniformly loaded circular area. Again this has been taken into a small strip or small dr and it has been integrated considering as a point load. Then we got a chart. This chart is your delta sigma z by cube divided by z by r. Once you know the radius of your circular area and distance below the ground surface where increase in stress has to be calculated, then we can calculate what is the increase in stress because of your circular loaded area. Then come to point, that is your vertical stress below the center of a uniformly loaded circular area. Then come to your vertical stress by a rectangular loaded area. Vertical stress by a rectangular loaded area. So, look at the figure here. This is your delta sigma z and it is coming your direction z. This is your x, say this is your y and this direction is your z. I am taking it. So, this will be dx and dy and this is your L and this is your B. This load has been distributed over uniformly over the rectangular area. So, I have considered a small area of size dx and dy. The area is having length L, width B. Then if I write it, dq is equal to q into dx dy, r square is equal to x square plus y square, then delta sigma z which is equal to p z q considering as if it is a Boussinesq point load 3 by 2 pi x square plus z square plus y square to the power 5 by 2 and this will be your zq. Then if I consider that particularly your P or maybe Q, loading intensity Q, then it will be P will be taken as small p or it is a Q, small p or it is a Q. Then I can write it 3 small q dx dy zq this P or Q over the area load intensity, capital P is your point load, small q is your load intensity. I can remove that small q. Now, if I convert it into P into P is equal to Q into dx dy, then it will be 2 pi and it will be x square plus y square plus z square to the power 5 by 2. So, delta sigma z, if I integrate over here d sigma z, so it will be double integration because dx has to be integrated over the 0 to L and dy has to be integrated over y is equal to 0 to b. So, it will be y is equal to 0 to b, then x is equal to 0 to L, then it will be 3q zq dx dy divided by 2 pi into x square plus y square plus z square to the power 5 by 2, which is equal to q into I. So, delta sigma z, if I am taking out the q, I is your influence factor. Then if I put it I, which is equal to, it comes out to be 1 by 4 pi into 2 mn root over of m square plus n square plus 1 divided by m square plus n square plus m square n square plus 1 into m square plus n square plus 2 divided by m square plus n square plus 1 plus tan inverse, I take the bracket 2 mn by root over of m square plus n square plus 1 divided by m square plus n square minus m square n square plus 1. This is the value of this. This m and n, m is equal to either b by z or L by z, which way you are taking, whether you put it L here b or b here L, does not matter. N is equal to either L by z or b by z. Entire chart is given. So, vertical stress in a rectangular loaded area, if there is a rectangular loaded area, what is the increase in vertical stress at this point, at the corner below this. You can superimpose, you can find it out also at the center, and these charts are allowed for examinations. Now, come to the next, that is your increase in stress or approximate stress distribution method. Approximate stress distribution method for loaded areas. These are all point load, then there is a strip load, line load, then there is circular load at the center, then rectangular load at the corner. Then if you want to find it out, suppose there is no chart, if you want to find it out approximate distributions, approximately what should be the value, it is called 2:1 method. It is called 2:1 method. So, if I put it in this way, this is B, this is 1 and 2, this is 1 and 2. Then for rectangular loaded area A, because it will be distributed with your 2:1, that means the variation will be 2 vertical to 1 horizontal. So, for rectangular loaded area, that means B by L and Q is equal to load intensity divided by meter square, then sigma Z is equal to Q B by L divided by B plus Z into L plus Z. Now, similarly for square shape, sigma Z is equal to Q into B square by B plus Z whole square. Similarly for strip footing, sigma Z is equal to Q into B by B plus Z. Sigma Z is equal to Q by B plus Z into B. This is what by means of approximate method you can do it, because this is a 2:1 distributions. So, if this distance is your B by means of 2 vertical and 1 horizontal, and if this is your height is Z, you can very easily find it out what is the width of this here. Then from there, based on that, you can find it out for 2:1 method, sigma Z what is there, for square shape what will be there, and strip footing what will be there. Now, based on your approximate method, there are two cases. One is your equivalent point load method, other is your, you can say that it is equivalent point load method. So, what is equivalent point load method? For example, this is the loaded area. This is my loaded area. In this loaded area, so you can name it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, divide the loaded area into small areas. Why it is called equivalent point load? For example, this is a loaded area, earlier it is same loaded area, rectangular shape, this will be B by L, this will be B by L. So, first principle is divide the loaded area into small areas. Divide the loaded area into small areas, and replacing the distributed load in each small area by an equivalent point load. Replacing the distributed load on each small area, then replace distributed load on each small area by an equivalent point load acting on the CG of the area. Suppose this is the area, try to understand. These are all distributed load over the area. Now, the entire area has to be, you divide the entire area into a small areas. I put it into a small area and it should be equally, do not put it unequal because it will be difficult. So, if you divide into 3 equal parts, suppose this will be b by 3, this will be b by 3 and this will be b by 3. Here it will be L by 4, here it will be L by 4, here it will be L by 4, here it will be L by 4. Equally you distribute small area. Then enter, suppose this distributed is 10 kilonewton per meter square, it acted over your B by L. Now this 10 kilonewton per meter square, this 10 kilonewton per meter square, this distributed load, then you distributed over small areas. So this is area B by 3 by L by 4, then that has to be distributed over this area. Then replace the distributed load. So this is the distributed load over this area into equivalent point load. Equivalent point load means, and that equivalent point load will act as on the CG. In mechanics of point of view, it is not going to be true. So what will happen if it is equivalent point load and this is a distributed area? So that means suppose there distribution of area, this is UDL is your Q, load intensity per unit area, into QL into B by 3 into L by 4. Why? This is my B by 3, this is my L by 4. So this is coming about to be point load Q1, equivalent point load. So this equivalent point load will act on CG of this area. So that is why it is called equivalent point load. So what will happen if I convert into here, make into here in this way, how it looks like? It looks like this way. So that means there is a Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, Q9, Q10, Q11, Q12, n number of. Then each point you calculate, each point, then this is a point load. For taking into this is a point load, then your Boussinesq's point load equation will come into picture. Boussinesq's point load equation will comes into picture. What does it mean? Sigma z is equal to point load Q1 into influence factor I1 plus Q2 into influence factor I2 dot 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 plus Qn into In divided by z square, which is equal to 1 by z square summation of I is equal to 1 to n, and this will be your qi and iz or I. So, basically distributed load has been converted into equivalent point load, and once you get equivalent point load, then from Boussinesq's equation by means of applied point load, you are going to find it out increase in stress, and it is the summation of all the point loads over your depth. That is why this is called equivalent point load. Now, we will analyze how equivalent point load will be effective for different cases. So, like vertical stress at any point under a rectangular area. It is at any point. Any point under a rectangular area means, if this is my rectangular area, generally what we have done earlier, if this is the rectangular area, generally by means of, if you go back to here, it is at the corner. So, it is not necessarily always should be at the corner. So, you can find it out, vertical stress may be here 1 point, 0.1, maybe sometimes it is not at the CG, somewhere else outside the rectangular loaded area 0.2, then it may possible along the line 0.3, then it may possible along the line 0.4. So, it is a vertical stress at any point under a rectangular area, rectangular loaded area at any point, right. Let us start with example. There are many examples I will continue, and also I will solve few problems. Let us start with an example, just try to understand. This is the case. Sometimes foundation has been made in this way. So, all the dimension has been given, let me name it A, B, C, D, E, F, G, H, and this is your 3 meter, this is your 3 meter, and this is your 4 meter, and this is also 3 meter. All dimensions has been given. So, it has been asked, find it out increase in stress at a point, this position, look at here, this is your point O at a distance here 1 meter below CB line. How you are going to do it? I have to make it into equivalent point loads. That means what will happen? Let me put it in such a way that, sorry, I say it is at a distance of 1.5 meter, 1.5 meter below this, and this is the where point we are going to find it out. I put it, this is 1.5 meter, right. This is your point O, and this will be, I take it at the center here, this is lying also center here. So, this will be your 2 meter and this will be your 2 meter, and this junction I am taking it as a L. Now, this is your M and it has been extended. So, if I remove this 1.5 meter, let me extend here, let me complete this one. So, this will be a B, J and K. How do I get it? How do I get it? Try to understand before I write it. This is my O, point O. If I consider this is a rectangular area, here you are getting at the corner. This is fine. This is one more rectangular area, here you are getting at the corner. This is one rectangular area where you are getting at the corner. Another rectangular area where you are getting at the corner. Then one more rectangular area where it is you are getting at the corner. And one more rectangular area where you are getting at the corner. Particularly for this rectangular area, if you look at here, this is overlap. I am taking this rectangular area, and if I take small rectangular area and if I take this rectangular area completely, this is a common. So, it has to be deducted. Then I put it, this is the rectangular area at the corner. My basic philosophy is I bring back this rectangular loaded area at the corner in such a way that I am getting this point everywhere else at the corner of the rectangular loaded area. Now, if I write it, area A, B, C, D, E, F, G, H, then I can find it out influence factor DMO. DMO, this influence factor DMO, this complete, plus OME N this is I, this is your N. IOMO, influence factor IOMO, straightforward, it is at the corner. DMEN, 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 sorry, it is not DMEN, OMEN, that means this is OMEN. In this case, it is straightforward at the corner, plus CIOL, CIOL, again perfectly fine, this is at the corner, plus LONF, LONF, this is also perfectly fine, plus AJOP, AJOP, this is your P, AJOP, this is also at the perfectly fine, plus POKH, 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 this is perfectly fine. Once you have considered, because this strip and this strip I am considering, this area is coming twice. Similarly, this strip and this strip I am considering, this area is coming twice. Then it has to be deducted, minus BJOL, BJOL minus LOKG, LOKG. This is how you are going to do it. I have only considered one of the point 1. One case I have considered. Next class I will consider 2, 3, 4, all typical cases, and also I will solve a problem. Thank you.